let's see. So last time I stated a special case of Bernstein's theorem, and actually a slightly false version of Bernstein's theorem. So let me tell you. There's just one thing that I didn't tell you about it, and so let me tell you it, and let me also tell you what the general statement is. Okay, so Bernstein's theorem says the following: says that the system of polynomial equations so you have n polynomial equations in variables, and so the system of equations, if things are generic, it's going to have a finite number of solutions. And the theorem says that the number of solutions is n factorial times the mixed volume of the Newton polytopes. And remember what we said is that for each one of these polynomials, you just take the exponents in the monomials. So for each one of these terms, you take the exponent and you plot that point in R to the n, and that's going to be one of the things you take the convex hull of to get the Newton polytope. And we said that the mixed volume was the number of solutions of this system, but there's a couple of catches. So one thing, isolated solutions. And here what I mean by isolated is what I mentioned briefly last time, that if the system is not generic, for example, if you look at the set of solutions to this system of equations, okay, well that's not a very generic system of equations, and so if you look at the solutions, then they form a curve, right? This is the real part of the curve, but it's a complex curve. And so those are solutions, but they're not isolated. And so you're isolated if there's no solutions around you. So when we say isolated solutions, we just mean points that are isolated. So these are isolated, but this is not isolated, something like this. So this yes, and this no. Okay, and the technical condition basically is that a solution is isolated if you can find a neighborhood around it containing no solutions, except for it. Okay. So that's the first catch, and it's not a very serious catch. And I already told you this last time, but what I didn't tell you last time is that this counts the number of solutions in it's not c to the n, but c minus the minus 0 to the n. Okay. So it counts solutions where none of the coordinates are 0. And that's really the true statement of Bernstein's theorem. Okay. If the coefficients are generic. Okay. No, and I'll show you why not. You actually need these conditions, and we'll see in an example why you need them. Okay. So the statement is clear. We talked about this last time. And what I want to do today is show you a very nice application of this. And so consider the permutahedron so surely this is your favorite polytope right now. It's so beautiful. At least you have to agree that there's a lot hiding in this polytope. It's kind of an amazing polytope. Convex Hall of permutations of, it's actually going to turn out to be a little bit easier if we do the permutations of 0, 1 up to n minus 1. Okay? Which clearly is not going to really make a difference. We're just shifting the polytope up. Okay? So let me tell you a beautiful, I think this is just beautiful, volume of the permutahedron. So think about it. The permutahedron is this very round thing with lots of vertices. It's actually not very easy to think about how to triangulate it, how to compute the volume. It turns out that the volume is n to the n minus 2. And this couldn't be simpler. It's beautiful, but especially if you've taken some classes in combinatorics, you have to love this number, because this is a number that appears in many different places in combinatorics. Does anybody know what this number counts? Actually, we talked about this number already, because we said that this is the number of spanning trees of the complete graph. And this equality, by the way, is not at all trivial. This is a beautiful inequality, and you will see a proof in Math 420 next semester. But what I want to show to you is why this formula is true for the volume of the permutahedron. Okay. So here's a lemma. Let's define delta ij to be just the segment between the unit vector ei and the unit vector ej. Okay, so it's just a line segment. So then I'm going to take the Minkowski sum of all these segments. Okay? So you have a bunch of segments. And choose two segments pointing in different directions, and you take the Minkowski sum of all of them. And the fact is that when you do this, you get exactly the permutahedron. Very mysterious, and let's see why that is. So why is that? Proof. There's a couple of ways of doing this. But generally, when you want to prove statements like this about Minkowski sums, it's useful to have inequality descriptions. And I'll show you how to do this in inequality descriptions. So what is the inequality description of pi n. Maybe before we do that inequality description, we should at least draw one of these examples. So let's say that n is equal to 3. Okay. So then we know that the permutahedron lives in R3, but it's really two-dimensional. Okay. And actually, it lives on this flat plane. The plane x plus y plus z equals 0 plus 1 plus 2, right? Because there are permutations of the numbers from 0 to 2. So if we look at the plane x plus y plus z equals 3, okay. So of course the coordinates here are 3, 0, 0, 0, 3, 0, 0, 0, 3, okay. Then this permutahedron is obtained by dividing each one of these segments into 3 equal pieces. Because, you know, here you're going from 0, 3 to 3, 0. So that means that that goes 0, 1, 2, and 0, 2, 1. Yeah. And then here and here, this is 1, 2, 0, and 2, 1, 0. And then here and here, these are 2, 0, 1, and 1, 0, 2. Okay. So those are the 6 permutations of the numbers 0, 1, and 2. And the permutahedron is this nice hexagon here. Okay. This is it. Okay, so this picture is familiar to you guys. Now let's do the inequality description. So first of all, we know that there is an equality, right? And that equality says that the sum of the variables, because this is a permutation of the numbers from 0 to n minus 1, we're going to get 0 plus 1 plus dot 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 until n minus 1. Okay, and that's the triangular number. That's n times n minus 1 over 2. Or it's easier to just say n choose 2. Okay. So that's the equality. Okay. Now for the inequalities, we need to specify. We get an inequality for each one of these facets, right? Okay. So we have 6 inequalities. And because you guys agonized over this picture, you can tell me what these facets correspond to in the permutahedron. Do you remember what the facets of a permutahedron correspond to? And do you remember what the normal vectors are? So remember that in your homework you had to show that the faces of the permutahedron were in correspondence with the ways of splitting up the set into subsets. And the facets correspond to the ways of splitting up the set 0, 1, 2 into 2 sets. Okay? Let me ask you, for example, what is this inequality saying here? If you are on this side of this hyperplane, what is your inequality? Well, it's just saying that the second coordinate is greater than or equal to 0. Right? Because here the second coordinate is equal to 0, and here it's larger than 0. So this is just x2 greater than or equal to 0. And what is the opposite one? It's here you see the, well, actually, let's do this one, x2 bigger than 0. Then this one is x1 bigger than or equal to 0. And this one is x3 greater than or equal to 0, right? These are kind of the 3 symmetric ones. Okay? And that corresponds to, for example, x2 greater than or equal to 0 corresponds to the partition where you do 2, 1, 3. Okay? Now, what does this correspond to? It's going to correspond to the opposite partition. 1, 3, 0. And what is the inequality then? I'm sorry? x2 less than or equal to 2. But I want to write it differently. You're absolutely right. I just want to write it differently. x2 less than or equal to 2. And you see it because it's a parallel hyperplane, right? But I want to write it as x1 plus x3 bigger than or equal to 1. And that's equivalent because x2 plus this is 3. So this is less than 2 if and only if this is more than 1. Okay. And similarly, this one says x2 plus x3 bigger than or equal to 1. And this one says x1 plus x2 bigger than or equal to 1. Okay? And the reason that I want to write them like this is that if you look at the inequalities of a permutahedron, what you're doing is basically taking all the different subsets and saying that that's greater than or equal to something. So the different subsets are x1, x2, x3, x1, x2, x1, x3, and x2, x3. And each one of these sums is bigger than or equal to something. Okay? And that's true in general, because in general, what you have is some kind of... In general, it's kind of impossible to draw this, but imagine that this is the permutahedron pi n. Okay? And here we have some facet. And then here, that facet corresponds to a partition where some of the variables are in and some of the variables are not in. And you're basically saying that the variables that are in, whatever they are, let's say x1 plus x3 plus x7 bigger than or equal to something. And then on the opposite side, there's a face that looks just like it, where the inequality is the other variables bigger than or equal to something. x2 plus x4 plus x5 plus x6 bigger than or equal to something. Okay. So that's basically a consequence of that homework problem. And so what you get is that for for each set S, you get that the sum of the variables in S is bigger than or equal to something. Okay. Now, what is it bigger than or equal to? For example, what is x1 plus x3 plus x7 bigger than or equal to? Think about it. How small could this be? If these are a permutation of the numbers from 0 to 6. y2? y3? y6? y... I mean, you're basically saying what are the... You need to plug in a permutation of x of 0 up to 6, and then try to make this as small as possible. So you're going to have to put 0, 1, and 2 in some order. That's basically the lowest that this could be. So this is bigger than or equal to 0 plus 1 plus 2. That's exactly right. And what about this one? Well, here you have 4 variables, so 0 plus 1 plus 2 plus 3. That's the smallest that it could be. And there are permutations that achieve these bounds, right? So those are the right inequalities. In general, what you get here is 0 plus 1 plus up to how many? Well, it depends how many elements are in this set. You have to stop at s minus 1, so that you have s things. And so this is cardinality of s choose 2. Okay? So that's the inequality description of the permutahedron. Okay. What is the inequality description of the simplex? Sorry, not the simplex, just this delta ij. Well, this is pretty easy, right? It's the points in Rn such that you're just going from I to j. So all your variables are 0 except for variable I and variable j. So xk equals 0 if k is not I or j. And what about the variables I and j? Well, you're doing the segment between 0 and 1. And so that means that the variables xi and xj have to add up to 1, because you're going from 1, 0 to 0, 1. And xi is bigger than or equal to 0, xj is bigger than or equal to 0. Okay, that defines the segment. And then all the other variables are just kind of garbage zeros that tagged along. So this is the inequality description of delta ij, but I want to write it a little bit differently, because I want to write it like this. So what is actually, let me use a k here instead of an I. That's good practice for what's going to come next. So, what is the sum of the variables x1 up to xn for this segment? Well, xi plus xj add up to 1, and all the other variables are 0. So, this is 1. Okay. Now, what happens if you add? So, if you take some subset of 1 up to n, and you add those variables, and this is bigger than or equal to what? Well, I'm going to make a similar argument and say that if I and j are in S, then this contains xi plus xj, which is 1, and all the other things are bigger than or equal to 0. So this is going to be greater than or equal to 1 if I and j are in S. Okay? But if I and j are not in S, then you can't really conclude anything out of these inequalities. You can just say this is bigger than or equal to 0. You don't know anything else. Okay? So I think it's clear that these inequalities imply these inequalities. Is it also clear that these imply these? It turns out actually that these inequalities are a subset of these, right? Because when S is the set I get xi bigger than or equal to 0. When S is the set j, I get xj bigger than or equal to 0. So the fact is that yes, these do. I mean, let me also say that if xi plus xj is bigger than or equal to 1, and if all the variables add up to 1, that means that all the other ones have to be 0. Okay? So this is implied as well. So these are two. You just have to look at it carefully, but these are two ways of writing in the same system of inequalities. Okay? Okay, so far all I did is write the inequality description of the permutahedron and of this thing. But now I want to justify this summation. Okay? And maybe to do that, it's good to see how this summation looks for this guy. So this is the permutahedron pi 3. Okay? And the question is, I mean, it's not really a question. It's a lemma that we're supposed to prove. But this lemma says that this is equal to the Minkowski sum of what? If you see, these are the 3 unit vectors, and then this is delta 1, 3. This is delta 2, 3. And this is delta 1, 2, right? This is the x1 axis, x2 axis, x3 axis. And so the three segments are delta 1, 2, delta 1, 3, delta 2, 3. So what we're trying to check is that this is equal to this plus this plus this. Okay? And this is fun. We like doing this. So first we add up this segment plus this segment. So we get this. And then we're supposed to add this segment. And then what we get to do is that we get to put one of these segments on top of each one of the points here. So then we sweep the thing like this, and what we get is exactly the right shape. Okay. So in this case it's true, and now I want to justify it in general. And what I want to do is the following. Maybe what I'm going to do is first do it very explicitly for pi 3, and then we'll see how it works out in general. So I'm going to make a table. x1 bigger than or equal to, x2 bigger than or equal to, x3 bigger than or equal to, x1 plus x2 bigger than or equal to, x1 plus x3 bigger than or equal to, and x2 plus x3 bigger than or equal to, and then x1 plus x2 plus x3 equals something. Okay. So in each row, I'm just going to write out the explicit inequality description of the corresponding polytopes. So for delta 1, 2, for example, you see we're saying that the sum is always equal to 1. Right? The sum of the variables equals 1. And then this greater than or equals, they're 0 unless they contain both 1 and 2. Right? That's what this is saying here. It's saying that the sum of the variables in S is greater than or equal to 1 if S contains I and J. Otherwise, it's greater than or equal to 0. So if I and J are 1 and 2, then all of these inequalities say something is bigger than or equal to 0, except this one, which is the only one that contains both 1 and 2. These are zeros, and this is a 1. Okay. You guys understand what is this table that I'm making? So for each one of these three polytopes, I'm just going to write the inequality description. And it's like this. Okay. So for delta 1, 3, again, all the variables add up to 1. That's universal because the variables add up to 1 for every one of these polytopes. So I can also put a 1 here. Okay. And these are all going to be zeros unless they contain both variables 1 and 3. So I get 0, 0, 0, 0, 1, 0. What about to describe delta 2, 3? Again, they're all zeros unless the 2 and 3 are both contained in the inequality. Okay. Now what about pi 3? Well, for pi 3, this is the system of inequalities, right? So the sum of the variables should be n choose 2. 3 choose 2 is 3. Okay. And for these guys, it's number of elements of S choose 2. So here I have only one variable, so I get 1 choose 2, which is 0, 0, and 0. And for these guys, I get 2 choose 2, which is 1, 1, 1. Okay? And so hopefully you see what I'm trying to get at, that I'm trying to prove that the sum of these polytopes is equal to pi n. And you almost want to treat this like an addition table and just add columns. Okay, and that's basically what I'm saying, that when you do this, everything works out beautifully like this. Okay? And actually, this is, once I say it like this, it's easy to see, because one thing that you should remember is that, and we proved it last time, that if the maximum value of a linear function c dot x in a polytope is, let's say, a, and the maximum value of the same function in Q is b, then when you do p plus q and you want to maximize the linear function in p plus q, then what you do is you choose a maximal guy here and a maximal guy here, and the value that you get is a plus b. Okay? And so it is true that if I want to know in this Minkowski sum what is the maximum value of this linear function, it is true that what I have to do is just add 0 plus 0 plus 0. So maybe really I should write it like this. I'm really going to add this. Okay? And then I'm saying that this remark guarantees that for the Minkowski sum, in this case I guess it's minimum value because I'm doing greater than or equal to something. So the minimum value of x1 is 0 plus 0 plus 0, which is 0, and so on. Okay, so these are really the correct minimum values for these inequalities. Okay. Now, imagine that. Let's see, how should I say this? Imagine that this was a bigger polytope, okay, so that n wasn't 3 but was a larger value. Okay. Then, okay, so let's pretend that this is bigger. And let's pretend that you had something like x1 plus x4 plus x7 plus x10 greater than or equal to, and you're trying to figure out what this greater than or equal to. Okay? When are you going to get zeros and ones here? So well, you should imagine this is bigger. So here I have all the different pairs from delta 1, 2, all the way up to, let's say, delta 9, 10. So here I'm assuming that n is equal to 10. So here I have all the different pairs from 1 to 10, and here I have all the different subsets from 1 to 10. What happens in column 1, 4, 7, 10? Well, in this column, 1, 2 is not contained in here, so I get a 0. But for example, when I get delta 1, 4, 1, 4 is contained in here, so I get a 1. Okay? And basically, I'm going to get a 1 in this column every time I get a pair contained in here. So delta 1, 4 gives me a 1, delta 4, 7 gives me a 1, but the other things give me 0. Okay? So in the end, when I add all of these things, how many ones do I have? Well, it's the number of pairs here, 4 choose 2, which in general, if this had size s, then it would be s choose 2, the number of pairs that you can choose. Okay. So that would mean that this polytope, the Minkowski sum of all these segments, has all the right inequalities to be the permutahedron. Everything matches up really nicely. I should say that there's one last thing to check, which is that there aren't any more additional inequalities. Okay, so the argument that I've made is that so far all the inequalities are correct. They are the inequalities of the permutahedron, and then you have to make a smaller argument to say that there aren't any other additional inequalities. That these inequalities fully describe this polytope. And let me just leave that as an exercise, that these are all the inequalities. I mean. So note, these are the inequalities of the permutahedron. So these are all inequalities of the permutahedron, and a little exercise is that there's no others. Okay. And that's going to show that these two polytopes have the same inequality description, and therefore they're the same polytope. Okay? Okay. So it's kind of a sketch of the lemma. Actually, I'm realizing now that I made a mess of this board, but if you look in the notes, I spelled this out more carefully. Okay? That's the lemma. And it's a beautiful lemma given the tools that we have. I think it's a beautiful lemma, period. I think this is a very nice fact. The permutahedron is the Minkowski sum of, if you realize these are precisely the edges of the standard simplex, right? In this case, I'm connecting these three unit vectors, but in general, the unit vectors form the standard simplex, and I'm just adding up all the edges of the unit simplex, and then when you do that, you get precisely the permutahedron. So that's a nice observation, and the corollary is that we have a new technique to compute this volume, because we know how to compute volumes of Minkowski sums. The volume is let me ask you something. What dimension is this volume? N? N minus 1? It kind of wants to be n, but it doesn't get to be n, because the permutahedron lives in n dimensions, but it's not n-dimensional. It's n minus 1 dimensional, right? And so, I mean, if I can compute this, but I'm going to get 0 because this permutahedron being n minus 1 dimensional, it does not have n-dimensional volumes. So the interesting question is, what is the n minus 1 dimensional volume? Okay. And then if you remember the way that Minkowski sum works, what you're supposed to do is take the mixed volumes of every possible n tuple. Actually, let me spell it out a little bit more, because I'm doing a step here. The volume of sum of ai pi from I equals 1 to m, the d-dimensional volume. Remember, we said that this was a homogeneous polynomial in the AIs. And if you want to know what the coefficient of AI1 up to AID is, it's the mixed volume of PI1 up to PID. And we're summing over all choices of I1 and ID. Okay? So what I'm asking you to do now is to take all of these AIs and set them equal to 1. Okay? So when you set those equal to 1, then you get the volume of the Minkowski sum. And in that case, all of this stuff is equal to 1. So then what I get is just the sum of the mixed volumes of every possible D tuple. Okay. So I get the sum of the mixed volumes of every possible, in this case I have n minus 1 things, so I need n minus 1 tuples, okay, of polytopes like this. So that means that I have to choose a delta 1 J1, then a delta I2 J2 up to a delta I n minus 1 J n minus 1. And I add up over all choices of I1 J1 up to I n minus 1 J n minus 1. Okay? Okay. And so now, here is the key lemma. The key lemma is that when you do that mixed volume, you get 0 or 1. One. Well, and just by what we're trying to do, you can kind of tell what this is going to look like. 1 if I1 J1 up to In minus 1 Jn minus 1 are a spanning tree of the complete graph and 0 otherwise. Okay. And let's parse this a little bit. So, for example, mixed volume of, let's say that n is 5. Okay. So here I have something like volume of delta 1, 4, delta 2, 5, delta 1, 2, delta 1, 3. Okay, that's one of the terms that appears. Right, I have n minus 1 choices of segments. And I'm claiming that this is either 1 or 0. And what I have to do is, well, if I write them like this, then maybe they look like edges of a graph. This is so what the lemma says is that you're supposed to just draw that graph. So you connect 1 and 4, you connect 2 and 5, you connect 1 and 2, you connect 1 and 3. And that happens to be a spanning tree, therefore this is 1. And if it hadn't been a spanning tree, you would get 0. So that's pretty cool, I think. And of course, the corollary of this and this is what we want. Right? Because if you have a sum of a bunch of numbers and the numbers are either 0 or 1, and they're 0, they're 1 if you have a spanning tree and you're 0 otherwise, then you're just putting a 1 for each spanning tree, so you get the number of spanning trees. Okay. So that's our plan. That's our plan for how to prove this. Okay, let's see how we're doing for time here. So I don't want to rush this argument, but one thing you'll realize is that we haven't used Bernstein's theorem today, right? And so it must be that I'm about to use it. I have this lemma about mixed volumes, okay, and Bernstein's theorem is something about mixed volumes. Okay? So that's going to be the connection with our strategy, and that's what we're going to do next time, is that we're going to use Bernstein's theorem to prove this lemma. Okay? And then I hope you agree that once I prove this lemma, then we'll be done with this proof of the permutahedron. But before we get to that, I wanna actually give you just a short discussion on a subtlety that's appearing here that is kind of hiding. And the point is an easy one. The point is a simple one, which is that when you compute volumes of things that are not full dimensional, then it can be a little bit tricky. So, and let me just give you a very simple example of this. Here's a polytope. Okay? So what is n times this polytope? Well, it's a segment of length, I don't know how long. How many lattice points am I gonna have? So this is 1p, then this is 2p, and this is 3p, this is 4p. Okay. What length would you say this is if you were being careless? How careless can you be? The most careless possible. 2. Why 2? 1, 2. Okay, I like it. Nice and careless. So that's called relative volume. Relative volume of P is 2. Okay. What's the point? The point is that what is the length of NP then, according to this? It's 2n, right? I have 2 and then 2n. Okay. So what is the number of lattice points in NP? How many lattice points are here? This thing has length 2n, which means that it's 2n plus 1. The point being that every time I put another copy of P, I get 2 more points. So two more each time, so I get 2 and then 2 and then 2 and then 2. Okay? So what's the point that I'm trying to make? The point that I'm trying to make is that this is the Ehrhart polynomial, right? The Ehrhart polynomial of the polytope is 2n plus 1. And I made this statement to you guys, and you believed it, that the leading coefficient was the volume. But if you see, actually, the leading coefficient is this careless volume, and not the real volume, which you might argue is 2 square root of 5. Yeah. So, theorem. Well, maybe definition. The relative volume of a polytope P in RD is basically, it's the volume, but it's rescaled according to the lattice along your flat. And so P is integral. Okay. The relative volume, this is supposed to be an R. The relative volume of P is the volume of P rescaled so that if you look at the affine span of P, the affine span of P, when you intersect that with the lattice, you're going to get some lattice. Okay? And in that lattice, you want that the simplest cubes have volume 1. Unit cubes have volume 1. Okay? So basically what I'm saying is if you're on this flat, then just call this length 1 because everything is off by a factor of square root of 5, and you can just, I mean, the point is that it's just a constant factor. So relative volume and real volume are just off by a factor. So just forget that factor and everything's going to be nicer. Okay? And okay, so then the real theorem, actually what I said last time was also real. If the Erhard polynomial, the leading coefficient is the relative volume. Now the thing is that if you look back at your notes, I always kept demanding that P was full dimensional when I stated this, and that was why. Okay, and if you are full dimensional, then the real volume and the relative volume are the same. But if you're not full dimensional, then this doesn't match. Okay, and then I can actually say what this coefficient is, which I hadn't said too carefully. It's don't forget, if you multiply or divide by 2, it's a half of the surface area, but relative surface area.